Hello everyone. Today we are going to discuss about the second problem of INMO 2025 which happened recently. So this problem is pretty simple. The system is that you are given with the sequence of numbers from 1 to till n, and you are asked to find all possible values of n for which you can reduce this sequence through a process to a single number. And what is this underlying process? You can choose two distinct numbers of the same parity, that is, two numbers which are odd or two numbers which are even, and you need to find the average and replace those two by that average. So by this process, can you obtain a single number? This is the question posed, and you are asked to find for the values of n for which it is possible. So initially this process might look simple, but I wasn't able to decipher a particular invariant in the process. The sum of numbers is clearly decreasing, and also I was trying to find a pattern in the reduction of a particular sequence. Maybe a particular sequence always reduces to the same number, and even that did not turn out to be true. For the sequence 1, 2, 3 till n, it indeed became false. I got different answers for the single digit number that I obtained through different ways. So the process is not very easy to handle. So let's take a closer look at this solution. Here is the question, and as you could see, the numbers are from 1 to n, and we go by the process of replacing two distinct numbers of same parity with its average, and we should end up with a single number. This is our goal, and we need to collect all such values of n. And they have even provided an example for n equal to 3 that it does not work. It's not our desirable sequence. The reason is that for 1, 2 and 3, the two numbers of the same parity are clearly 1 and 3 as they are both odd, which can be reduced to 2, 2. Now both 2 and 2 are of same parity, but they are equal. And as I mentioned earlier, you have to select two distinct numbers. So thus we cannot proceed further. And also there are no other pair of numbers with same parity and distinct in the initial sequence. So this is the only process by which we can go through, and it ends up with two numbers. Thus n equal to 3 does not work. Let's try for n equal to 5. For 5, we have 1, 2, 3, 4 and 5. And let's say we select 3 and 5, and the average of them is 4. So 1, 2, 4 and 4 will be the next sequence, and we then select 2 and 4. Then we obtain 1, 3, 4. And then we select 1 and 3 as they are both odd to obtain 2 and 4, and 2 and 4 directly gives us 3. So it is possible for us to reduce n equal to 5. Let's call this sequence of moves to be R. It's just a way to denote this sequence of move for n equal to 5. So here is one beautiful observation that I was able to make. Suppose you have the sequence like 1, 2, 3 and so on. If you increase every number by the same constant, then the process will take you to the final step also, which is increased by the same constant. Say for example, here each number is increased by 2. Then we get 3, 4, 5, 6 and 7. Now by following the same process, you will end up with 5. The reason is because the parity won't change and the average will also be shifted by 2. And therefore, we will end up with the number plus that constant, which is 5. Let's call this to be S, the sequence of moves to be S. And let's call the sequence of moves starting from 4, 5 all the way up to 8, totally 5 numbers, which will clearly end up with 6 because it is 1 raised from the sequence S. And let's call the sequence of moves to be T. So have in mind that we will incorporate these sequence of moves in our solution. Okay, so let's make a rigid claim. The claim is that for n greater than or equal to 10, it is possible to reduce the sequence 1 to n to a single number, and even the value can be determined, which is n minus 2. So it's possible to reduce it to n minus 2. And mind you, this doesn't mean that you cannot reduce it to any other numbers. So n minus 2 is possible, that's what we claim, and let's prove it. First we will prove the base case. What are the base case that we are going to take? So we are going to use induction in order to prove this. So we need to prove the base case first and then the induction step. The induction step is quite easy. So we will concentrate more on the base case. So first, for n equal to 10. For n equal to 10, the underlying sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And let's apply T. What is T? 4, 5, 6, 7, 8 reduced to 6 is called as T. So thus all these numbers can be replaced by 6. So I am going to do that. 1, 2, 3, 6, 9 and 10. And suppose we choose 2 and 6 and replace it with 4, we then get 1, 3, 4, 9 and 10. And suppose we take 1 and 3, then we get 2, 4, 9 and 10. And we take 2 and 4 and ensure that the numbers are of same parity, otherwise you may end up with a decimal number. 3 and 9 average out to 6, so you get 6, 10, and the average of 6 and 10 is 8. And voila, we have reached the final number 10 minus 2, which is also equal to n minus 2. Next we will go to n equal to 11. Let's write the entire sequence. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we perform R here. What's R? R is the reduction of 1, 2, 3, 4, 5 to 3. So replace it with 3 and you get 3, 6, 7, 8, 9, 10 and 11. And then you choose 6 and 8. You may reduce it to 7 and choose 3 and 7. You can reduce it to 5. So we then get 5, 7, 9, 10 and 11. And 5 and 7 average out to 6. So you get 6, 9, 10, 11. And then we choose 6 and 10. That goes to 8. And 9 and 11 goes to 10. So 8 and 10 goes to 9. And again, which is n minus 2. 11 minus 2. So n equal to 11 also satisfies the claim. Next, n equal to 12. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. And over here, let's apply S. That starts from 3. 3, 4, 5, 6, 7. So we replace it with 1, 2, 5 and 8, 9, 10, 11, 12. And suppose we choose 5 and 9 to get 7, and we get 1, 2, 7, 8, 10, 11 and 12. And here we choose 1 and 7 to get 2, 4, 8, 10, 11 and 12. And here we may choose 4 and 8. 4 and 8 will give you 6, and 2 and 6 will give you 4. So thus we get 4, 10, 11 and 12. Now we select 4 and 12, and the average of it is 8. So we get 8, 10 and 11. Now 8 and 10 reduces to 9 and 11. 9 and 11 can be reduced to 10, and voila, we got n minus 2 again. So now this almost completes 50% of the solution, because the base case will include n equal to 10, 11 and 12. Now we will use the induction step to proceed further. The induction step is the following. If the claim works for n, then it works for n plus 3. Because suppose you are able to reduce the first n numbers from 1 to n to n minus 2 as per the claim, then let's see what can be manipulated in order to arrive at the desired result for n plus 3. So we convert the first n numbers to n minus 2, and then we have n plus 1, n plus 2 and n plus 3. And over here we choose n minus 2 and n plus 2. The average of these two is n, because they are of same parity. I may choose them, and of course they are distinct. And we also choose n plus 1 and n plus 3, which will give us n plus 2. Now n and n plus 2 are of course of the same parity, and their average is n plus 1, and therefore we have proved that n plus 3 length sequence can be reduced to n plus 1, which is 2 subtracted from n plus 3. And therefore we are done by induction. That is, it works for 10, 11 and 12. Therefore the claim works for 13, 16, 19 and so on. You may keep on adding 3, and for 11 you may keep on adding 3 to get all the corresponding numbers, and for 12 you can add 3 to get the corresponding numbers, and altogether they comprise of all natural numbers starting from 10 to infinity. Thus by induction we have proved that it works for all natural numbers greater than or equal to 10, keeping the base case as 10, 11 and 12. So this step, these jumps are by our induction step. Alright, so how about the remaining numbers? Well, the remaining numbers are too less and easy to compute, so let's do them manually. So for n equal to 2, it's just 1, 2, which will not work, cannot be reduced. For n equal to 3, it was given in the question, and that's the only possible move. For n equal to 4, you have 1, 2, 3 and 4. Now the only possible two moves is by choosing 1 and 3 to convert it into 2, and 2 and 4 to convert it into 3, and 2, 3 cannot be reduced further. and there are also no other procedure through which you can go. And for n equal to 5, we just saw it is the step R. Through the procedure R, you can get to the number 3. For n equal to 6, you may try with different possible procedures. Say you reduce the first 5 numbers to 3 by the step R and you get 3, 6, through which you cannot proceed. And suppose you go by including the 6 initially. So 4, 6 can be converted to 5 to get 1, 2, 3, 5 and 5. And 3 and 5 or even 1 and 5 can be combined to form 3. So you get 2, 3, 3 and 5. And again you can select 5 with 3 to give you 4. So you get 2, 3 and 4. Now 2 and 4 gives you 3, 3, and which cannot be processed further. And maybe you choose 6 and 2 instead. Then you will get 1, 3, 4, 4, 5. And suppose you choose 1 and 5, and that gives you 3, 3, 4, 4, and that's it. You cannot proceed further. So try to do all possible procedures so that you are exhausted with all of them. And you can easily realize that for 6, you will not be able to reduce to a single number. Okay. Then for 7, well, for 7 you can have 1, 2, 3, 4, 5, 6 and 7. And suppose you reduce it by choosing 5 and 7 and you get 1, 2, 3, 4, 6 and 6. And then you choose suppose 4 and 6, you get 5. 1, 2, 3, 5 and 6. And then you choose 3 and 5 to get 4. So you get 1, 2, 4 and 6. And then you choose 2 and 4 and that gives you 3. So you get 1, 3 and 6. Now you choose 1 and 3 to get 2 and 2, 6 gives you 4. Thus it's possible for 7. We may reduce it to a single number which is 4. And for n equal to 8, 1, 2, 3, 4, 5, 6, 7 and 8. Since it works for 5, through R you can reduce it to 3, 6, 7, 8. And now you may choose 3 and 7 which gives you 5. And 6 and 8 gives you 7 and 5, 7 gives you 6. So it's possible for n equal to 8. Now for n equal to 9, you have to be a bit careful. 1, 2, 3, 4, 5, 6, 7, 8 and 9. Let's implement S here. What is S? S starts from 3 to 7 and it converts it to 5. So we get 1, 2, 5, 8 and 9. And say you choose 5 and 9, we obtain 1, 2, 7 and 8. Say you choose 1 and 7, we get 2, 4 and 8. And now we choose 4 and 8, that gives you 6 and 2, 6 gives you 4. Thus it is possible for n equal to 9. So we have checked all the numbers from 2 to 9. So let's write down. The numbers that work are just 5 and 7, 8, 9. And it clearly works for all numbers greater than or equal to 10. Therefore, the set of numbers for which it's possible to reduce to a single number is 5 and n greater than or equal to 7. Because from 7, all the consecutive numbers satisfy the desirable condition. So thus we have found all possible values of n, and we have disproved for the other values of n that it is not possible to reduce to a single number. So you have to be a bit careful about n equal to 7. You cannot always reduce n equal to 7 to a single number. So a careful handle is recommended. There can be multiple easier solutions, and I hope there is one. If you find one, please mention in the comments and let's discuss more on that. See you in the next problem. Thank you everyone. Bye.